The Standard Model describes all known elementary particles and interactions except gravity. Its symmetry structure is based on the gauge group SU3C cross SU2L cross U1Y. We will follow a sequence of increasingly unified symmetry groups. Starting from the Standard Model symmetry, we will see how it can be embedded into SU5 and then into the larger group SO10. These groups play a central role in grand unified theories, which attempt to describe apparently different interactions within a common mathematical framework. The symbols SUN and SON denote Lie groups, which are continuous symmetry groups represented by matrices. The integer n specifies the dimension of those matrices. The letter U stands for unitary. Unitary matrices satisfy U dagger, U equals I, which preserves inner products and therefore probabilities in quantum mechanics. The letter O stands for orthogonal. Orthogonal matrices satisfy O transpose, O equals I, which preserves lengths and angles. The prefix S stands for special. For unitary groups, it imposes the condition determinant of U equals 1, removing an overall phase. For orthogonal groups, it imposes determinant of O equals 1, selecting pure rotations and excluding reflections. The Standard Model is built from 3 symmetry groups. The subscript C, L, and Y refer to color, left-handed weak isospin, and hypercharge, respectively. The symbol cross denotes a direct product. This means that the 3 symmetry groups act independently. An element of the Standard Model symmetry consists of one element of SU3, one element of SU2, and one element of U1, acting simultaneously but independently. A natural question is whether these 3 separate symmetries can be understood as parts of a larger symmetry. Historically, unification has often revealed deeper structures in physics. Maxwell unified electricity and magnetism into electromagnetism, and later the electromagnetic and weak interactions were combined into the electroweak theory. There is also a practical motivation. The Standard Model contains many independent parameters. A larger symmetry can relate quantities that otherwise appear unrelated, leading to a more economical description of nature. The group SU5 provides the simplest realization of this idea. It is the smallest simple Lie group that contains the Standard Model symmetry as a subgroup. Instead of 3 independent symmetry groups, one may regard them as different aspects of a single larger symmetry. To understand what the embedding into SU5 means, consider a 5-dimensional complex vector space. A vector V in this space can be written as a 5-component column vector. An element U in SU5 acts on this vector through matrix multiplication. V goes to UV. Now consider matrices of the block diagonal form, where A is in SU3 and B is in SU2. The first 3 components of the vector transform among themselves under SU3, while the last 2 components transform among themselves under SU2. Because the off-diagonal blocks vanish, the 2 sectors do not mix. This provides a concrete realization of how the Standard Model symmetry can be embedded inside a larger SU5 symmetry. The idea of unification can be extended further. The group SO10 contains SU5 as a subgroup and provides a remarkably compact description of matter. One generation of Standard Model fermions, together with a right-handed neutrino, fits into a single 16-dimensional spinor representation of SO10. When viewed from the perspective of the SU5 subgroup, this representation decomposes as 16 equals 10, direct sum, 5 bar, direct sum 1. The singlet 1 is naturally identified with the right-handed neutrino, while the representations 10 and 5 bar contain the remaining fermions of one Standard Model generation. Understanding why this decomposition occurs and how such decompositions are determined in general will motivate much of the mathematics developed in the following videos.